Hello, everybody. So this week we're talking about high dimensional data, and I grew up watching Teenage Mutant Ninja Turtles, and in Ninja Turtles they're always fighting bad guys from another dimension. Well, not always; they're normally fighting Shredder, but routinely people from the next dimension or another dimension were coming, right? And um, I I was going to say we're not talking about dimensions like that, but we kind of are, right? This idea of dimensions comes from the fact that we live in a world with three dimensions. Let's not include time, right? And the point is that I can move stuff in the front to back dimension and not change it in the left to right dimension or the up and down, right? These dimensions are independent. They're independent ways of describing something's position. If I want to say where something is, I need to give three values, right? Now, I can, if I restrict myself to working on a piece of paper, right, now I can only give it in two dimensions. That's our XY scatter plot, all right? So we are, so this idea of dimensions in our data and dimensions in the real world are related, right? They're, they're the amount of data we need to describe something. Now, I'm going to talk about dimensions and I'm also going to talk about features, and these are fundamentally the same idea. Um, but when I'm talking, typically I talk about dimensions in like an abstract sense, that your data might have five dimensions. And when I'm talking about a feature, I'm typically talking in a concrete sense, these features, that feature, you know, um, because it just sounds weird sometimes to say that dimension to me. But these are the same ideas. They're how many data points you need, or how many measurements, sorry, you need to describe a data point, right? So, um, you take a measurement of a mouse and you might need to know its age, it's what dose or drug it's on, and its performance. You have three dimensions in your data set. And we're talking about this because a lot of data that we get these days has a very high number of dimensions, right? So Jack Ordes gives me these data sets at the moment. They have like 40 or 50 dimensions, right? It's a real pain. It is a pain, right? And people talk about high dimensional data because it's got all sorts of problems with it, all sorts of annoying behavior. And we're just going to be fundamentally dealing with one of them, right? And that is that it's hard to visualize, right? That when you collect new data, in my opinion, and the opinion of many others, that the first thing you should try and do is visualize it, try and get an idea of what is going on. Um, I would argue that you should do that before you try and do any statistical tests, because if you don't know what your data looks like, then your statistical tests could be highly misleading. Okay, but visualizing high dimensional data is not easy. All right, with two dimensional data, you just do a scatter plot, x versus y, no problem. I mean, it's straight away, even by the time you get three dimensions, which you can in fancy graph packages plot three-dimensional data and you have to spin it around and it can be very hard to grasp. But beyond that, you're in trouble. And I sort of gave this example in the text talking about this real life cancer cell data set where you can, if you're clever enough, be almost perfectly accurate in predicting which, from looking at a cell, is it cancerous or not. But it is very hard to figure out how that's possible when you just look at the data. Every time you compare any two pairs, or at least most of the pairs, there seems to be a huge overlap. Maybe they're a little different. Maybe the means are separated. If you did a t-test, it would be different. But you can't cut a line and say everything on one side is cancerous and everything on the other is benign. Um, and the truth is, there is a way, but it is very difficult. So we're going to be talking about, you know, the first step that we can take in visualizing high dimensional data, which is the PCA, the principal component analysis. So let's just load some not ridiculously high dimensional data, but you know, borderline data. Right? It's four-dimensional data. Well, at least the bits we're going to be looking at, right? So we're going to load it. We're going to make our data frame with the read CSV file. So we've got our data frame there on the left. We're going to put into it the output of this function, read.csv, and we're going to open our quote marks because we're going to put in a string, which is a web address. http://billconnolly.net/data/penguins.csv. Hopefully I did that right. Press enter. Okay, no errors came up. Let's go use our head function just to see what we have here, and we've got this data here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 raw dimensions of data. All right, that's a bad scene. Now, because of where we're going to go, I just want these real numerical values. This bill length, bill depth, flipper length, and body mass. In a perfect world, we're trying to visualize all these other things. Maybe there's important information in the island information. Maybe there's important information in the year or in the sex of the penguin, but we're not going to do that, right? So we're just going to take a copy of our data frame with those columns we want. So we're going to go make a new variable called D for our data frame, and we're going to get our original data frame, and we're going to use the square bracket notation to pull out specific columns. And we remember, right, that it goes like row, comma, column number, but we want every row, so we leave that blank. And then which columns do we want? We want 1, 2, 3. We want 4, 5, 6, and 7. 4, 2, 7. And we press enter. And let's see if that works. So we're going to go head D, and there they are. All right. Now, 4 dimensions, as I said, this is already pretty difficult to visualize, but it's not ridiculous. Like, I can make a graph comparing them, and I can do that with this nice little inbuilt function of R called pairs. And if I go pairs of D, we get this graph here, right? Well, my head's vaguely in the way, apologies, right? And first time you look at this, it's pretty confusing. But what it's saying, let's look at this graph here. This is bill length against bill depth, okay? This one here is bill length against flipper length. And this one here is bill length against body mass, right? And these graphs here and here are representing the same data, but on this one, bill length is on the y-axis and bill depth is on the x, while on this one, bill depth is on y and bill length is on x. So this and this are the same graphs, they're just rotated around. Now, we're going to be talking about clustering next week. I'm not going to get into it now, but you can start to see the concept of clustering, right? The question is, do these measurements suggest there are different populations, different clusters of data, different clouds of data, or is it all one big cloud? If this one here, let's say this was the only data set we had, it would start to look like maybe there was just a big cloud, though you can kind of see there's a little gap separating the two, so maybe there are two. But of course, we've got all of them. Now, we can, quick and dirty, add colors to this. If we go PSD and I go col for color, and it is equal to, and we do this little trick, we go as factor, and we go back to our original data frame that has species as one of its columns. Remember, we can also use this $name notation, and we press enter, we get them colored. Now, I need to get in the full details here, but what's happening is as factor is turning those strings, Adelie, I forget what they all are, rock hopper, into numbers, 1, 2, 3. And so our as factor turns the species into numbers, and then the numbers get fit into the column, the color. So every data point gets the same color for the species. Even though we don't have a little legend, we can now clearly see that, there is clearly clusters in this data. The green one typically sits off by itself, whatever species that is, and the red and black ones sometimes are well separated and sometimes sit on top of each other. Okay. Now, as I say, with 4 dimensions, we can use pairs and we can see this, right? And we can painfully, but we can slowly and carefully make sense of this data and see that there are well separated clusters, and that this data looks kind of sensible-ish, which is to say it doesn't Like there are no huge outliers, and does it make sense that the body mass is between 3 and 6,000 grams, 3 and 6 kgs? Yes, it does. That sort of feels believable. The flippers are between 170 and 230 mils. Oh, yeah, that seems pretty sensible, right? So all this data looks sensible. We can see the structure of the data. We can, start to think about what we might do with this data now that we've collected it. But this data had 50 dimensions, right? This pairs would not be plausible, and we'd have to do, hundreds of even pairs to compare every single property, every single feature uh, against every other feature in a way that we could see the results. So we don't want to do that, right? So let's imagine we have data like that. We've got, greater than 10 dimensions. We still want to know what's going on. Are our is all of our data sitting all on top of each other, or is it are there separate groups, and are there any dimensions that are kind of useless that we don't even really need to consider? And so with that, we're going to do PCA, principal component analysis, right? And I talked about that in the text quite a lot, but we'll go through it again. All right, that the PCA has some pretty clever maths. It's old. It predates computers, right? Goodness knows how they did it when it was first invented, but it basically imagines your data is a sausage. All right, now it doesn't. It's not. This is not like a t-test where I say, this is meaningless if your data doesn't have normality, right? If it breaks these assumptions. It's more just the PCA is not going to be as useful. It's still going to work, and its output will still be true. It's not going to do a great job if your data is not vaguely sausage-like. And what I mean by sausage is we could call it an ellipsoid. It would be a slightly fancier term, a high-dimensional ellipsoid, which is to say, let's imagine we have 3D data. What you want is your data to sit along some long axis, and then the data to be sort of around that long axis, that axis of maximal variation, where a lot of the data points are collinear, right? And we see that here in like flipper length versus body mass, right? The data here is collinear. Flipper length and body mass is collinear. If one gets bigger, the other one tends to get bigger. And so in reality, we don't need to know both of these, right? They give us kind of the same information. Exactly what we mean by information gets kind of complicated, and I'm not going to get into it. But you can easily imagine, right, if we had a big data set of subjects, right, and it had their body mass in kilograms and in pounds, right, that data would be perfectly collinear. We could absolutely predict what one is from the other. If you knew it in pounds, you could get it in kgs. And so we don't need both of those. They are useless. They add nothing to us by having both. We just need one. And so PCA basically hunts out collinear data while it's also hunting out this axis of maximal variation. And what it does is it takes our axis of maximal variation, it grabs our whole sausage, and it rotates it so that that axis of maximal variation sits along principal component 1. Now, I've got animations in the online content that sort of show how it does that. It basically fits a line to that axis of maximal variation, and then the data is projected onto that line, and that's how we get the first principal component. And then the second principal component is some vector, some line that is at 90 degrees to that, but the second highest variation. So it must be 90 degrees to the first principal component, but whatever 90-degree line to that has the axis of maximal variation, that becomes the second principal component. So the data is then projected onto that one, and so on it goes, right? And it actually does this, it doesn't do it in a sequential way like I've described. It does it all in one big step, thanks to the magic of maths, and the data gets projected onto these principal components. And if your data is a nice sausage, then a nice ellipsoid, then it will do a great job of saying you don't need all of these other dimensions. They don't add anything, so if we had these columns that were kilograms and pounds of each subject, it would say, look, we don't even need that last one. Okay, so we've got our data here. In the next video, I'm actually going to go through, we're going to run our PCA, we're going to have a little look under the hood, just ever so briefly, and hopefully it won't be too scary to get this to run.